Hello everyone, I'm Umesh Kashyap from the Indian Institute of Technology, Bhilai. Today I will present our work GAN-Invert, Unveiling Vulnerability in Privacy Preserving Facial Transformation. In this work, we investigate a fundamental security question. Are deep learning based privacy preserving facial transformation method truly secure against reconstruction attack? Let me first provide some background. Deep learning based privacy preserving method or DLP aim to protect facial identity before images are shared on the public platform. This basic idea is to transform original image into protected image where the person identity is hidden but task related information is preserved. This allows downstream tasks such as attribute classification, expression, recognition, and age estimation to continue working accurately. For example, here we shown a image of Bill Gates protected using the DLPP method. When this protected image is given to attribute classifier, the system can still correctly predict facial attributes like gender, eyeglass, smile. However, when the same protected image is given to facial recognition system, the identity recognition fell. This demonstrates the intent goal of the LP method, preserving utility while hiding identity. However, important security questions remain. If someone shared their protected image to internet, an adversary have the access of this protected image. Can adversary reconstruct and recover the true identity of the protected image? There are a lot of protection methods which adversary can recover or not. The question is remain unanswered still. So this motivate our work. So our work has two objectives. First, we perform comprehensive security evaluation of state-of-art DLPP method against reconstruction attack. Second, we propose a reconstruction framework called GAN-Invert, which learn to recover original face information from protected image and evaluate the actual vulnerability of these privacy preserving methods. So threat model, now I briefly explain our threat model. We consider critical scenario where user upload protected facial image to public platforms such as social media or cloud service for performing different tasks. The attacker objective is to recover the original facial identity from this protected image. We assume strong but realistic oracle setting where the attacker knows the deployed DLPP transformation method. However, the attacker does not have access to the original private image. The attacker can collect publicly available protected image and also utilize large-scale public face dataset to train surrogate reconstruction model. Using this information, attacker attempt to learn the inverse mapping from protected image back to the original image. Now I will explain the working mechanism of GAN-Invert. To train our generative reconstruction model, we first create a surrogate training dataset containing pair, original, and protected image. The protected image is given as an input to the generator, which produces a reconstructed face image. The reconstructed image and original image are then passed through the pre-trained face recognition model to extract identity feature. The difference between these features are used to calculate the feature level identity loss, which help preserve identity information. Next, we calculate the pixel level reconstruction loss using the mean square error between the original and reconstructed image. Additionally, both images are passed through a discriminator, which provide adversarial feedback and encourage the generator to produce realistic facial image. To preserve semantic facial transformation, we extract attribute feature from both image and calculate the attribute consistency loss. Finally, these four losses are combined to optimize the generator parameter. This training process continues until the model learns to update inverse mapping. After training, the learn gain invert model is directly applied to unseen protected image to evaluate its reconstruction capability and generalization. We evaluate GAN-Invert on three widely used face datasets, CELEB-HQ, FFHQ, and LFW. We considered 10 representative DLPP methods covering four major categories: pixel level manipulation, gain-based adversarial makeup, feature disentanglement, and reversible encryption-based method. To measure identity leakage, we evaluate reconstruction image using two state-of-art face recognition model, arc face and cos face. For reconstruction quality evaluation, we use PSNR, SSMI, and LPIPS. Finally, we compare GAN-Invert with existing reconstruction approach, including master gain and phantomas. Before comparing different DLPP method, we establish the evolution condition. So different privacy method naturally provide different level of distortion. Therefore, we adjust each method parameter to achieve the same downstream task accuracy of 89%. This allows us fairly comparison of privacy vulnerability under similar utility condition. The table shows the corresponding pixel distortion represented by delta and semantic distortion represented by epsilon. For all evaluated DLPP method, this standardization ensures that our security analysis is not biased toward method that simply introduce more distortion. Here we present quantity reconstruction result. Although DLPP method significantly modify the original face appearance, GAN-Invert is able to recover the important facial characteristics. For several privacy methods, the reconstruction image preserve facial structure, identity-related feature, and visual appearance. For weaker method, uh, the reconstruction images are visually very close to the original faces. This quantity result further validate our visual observation across all three datasets. GAN-Invert consistently achieve high PSNR, high SSMI, and low LPIPS value. This indicates that reconstruction image maintain strong visual similarity with original image. However, reconstruction quality alone does not fully represent privacy leakage. Therefore, we also evaluate whether the reconstructed image can recover the original identity. This figure shows recognition accuracy using arc face and cos face. While the protected image significantly reduced recognition accuracy, reconstructed image generated by GAN-Invert achieve higher recognition performance. This demonstrates that GAN-Invert is capable of recovering identity information from protected image across different privacy protection methods. Next, we analyze the impact of different generator architecture. We compare standard CNN architecture, ResNet encoder decoder, and UNet architecture. Among these architecture, UNet achieve a best reconstruction performance. This is mainly because skip connection allow the network to preserve fine-grained facial detail during the reconstruction. We also study the impact of training data size. As expected, increasing the training data consistently improve the reconstruction quality and reduce the convergence time. We compare our GAN-Invert with the existing reconstruction approach. Master key gain is designed specifically for one privacy method, AVH. Even under this limited setting, GAN-Invert achieve better identity recovery performance compared to the master key gain. Phantomas provide a more generalized reconstruction framework, but it achieves only 10% recognition accuracy under our evaluation setup, where our GAN-Invert achieve approximate 87% recognition accuracy. Furthermore, when we train Phantomas target defense, GAN-Invert still achieve 93.6 recognition accuracy, outperforming Phantomas which achieve around 88.3%. To conclude, our study demonstrated that mainly existing DLPP method remain vulnerable to reconstruction attack. Although these attacks successfully prevent directly identify recognition, they often achieve privacy through identity obfuscation rather than completely identity removal. Among these evaluated approach, the Stangle ID Riddle provides stronger protection as they replace identity information instead of simply perceived facial feature. Our finding highlight that future privacy preservation should focus on achieving higher semantic distinction while maintaining the low pixel distortion to provide strong and more reliable privacy guarantees. These are the some reference of our work. Thank you very much for your attention. If you have any question or comment, please feel free to contact me through this email address shown on this slide. I will be happy to answer your questions.